Welcome to the mini course Quantum Riemann-Roch by Alexander Givental. Could you please take the conference?
Okay, thank you. If you remember, in the end of the previous meeting, we discussed this theorem by Faber and Penderipanda, which describes what's called the Hodge integrals, how to bring into Gromit theory, in the intersection theory on modular space of stable maps, bring in new classes, Chern components of the Chern character or any other characteristic classes of the Hodge bundle. And it turns out that so the dependence on this parameter, this k, so is governed by some system of differential equations in a straightforward generalization of the result of Mumford from 1983, just set up in the convenient language of generating functions. And they said that this, if you look carefully at these differential operators, then you know that the combinatorics is not very complicated, and it rather suggestive of some language which makes these operators particularly simple and meaningful. And so now let's discuss this language. The name of it is symplectic loop space formalism. So the input data for this to set up this formalism is vector space H equipped with some symmetric non-degenerate pairing and a non-zero vector V, which is referred in the formalism as the Latam shift. But in reality, it will be so that H will be the cohomology of the target space with coefficients in the ground ring, which is a Novikov ring. So these Q variables are needed in order to distinguish contributions of curves of different degrees into the generating functions. This pairing will be the Poincaré pairing, so that's really, it's not a space H, but a super space, and actually it's a module over this Novikov ring. And this vector V will be just a unit vector in the cohomology algebra. Now, the loop space, it's not a loop space of the target space, it's a loop space of this cohomology space. So it is this curly H, it is the space of Laurent series in one indeterminate Z with vector coefficients in this finite dimensional space H. And that letter Z is, we encountered it with many, well, several times, and it has different meanings. It was, well, if you look what we discussed last time, it was a placeholder for psi classes in the intersection theory in the Riemann spaces. But if you go back to the heuristics of Sesson equivariant Floer theory on the loop space of the target space, then we're talking with you about this semi-infinite Floer homology as one equivariant of the covering of the loop space. And actually it had that very same, essentially the same form as that curly H space. Now it is that Z, it was a generator in the cohomology, equivariant cohomology of the point over S1. So it was that equivariant parameter that corresponds to rotation of all loops. But and this was also Novikov ring where Q's were deck transformations, and except that I was using real coefficients that time rather than rational. This time it is more or less the same. I think therefore we so the space we encountered at that time in some heuristic theory, heuristic approach to Floer theory. Now we have it just because we want to have it, and Z is just a letter. In this moment not supposed to have any special topological meaning, but so in this space we can introduce the symplectic, the anti-symmetric bilinear form, which plays the role of symplectic structure. Namely, if there are two Laurent series F and G, we can change the sign of the argument in one of them, pair the coefficients using this intersection pairing. It will be scalar valued Laurent series, and take the coefficient at Z inverse, so this residue here. And because this minus and this extra z, this extra dz, it is an anti-symmetric bilinear form. And it's non-degenerate, it's a symplectic structure and very simple one. So namely, if you think of Q0, Q1, Q2, etc. as coefficients at, so it's kind of coordinates on the space of power series in Z, then so that 1 z square are is a basis in the space of power series, and minus 1 over z, 1 over z square, minus 1 over z cube would be the Darboudou monomials with respect to the symplectic structure. So it's kind of very simple. Moreover, it's clear from this form of the symplectic form that the space H plus, which is power series on this picture, therefore this space of Laurent series consists of power series, and the principal part of Laurent series and power series form Lagrangian subspace, and there is no pole here, and the principal parts also form Lagrangian subspace. There is no coefficient at 1 over z in this expression, and therefore this whole symplectic loop space can be, by this Lagrangian polarization, this decomposition into this direct sum of Lagrangian subspaces, can be identified therefore with a cotangent bundle of this H plus of the space of Laurent series, space of power series. Now what we call the total descended potential stem, it is this generating function e to the sum over all genera of this Planck constant that keeps track of earlier characteristics of the curves of genus G, and Fg it is the generating function for genus G descended invariants. So this expression actually, all these functions are functions of or naturally functions on H plus, and therefore you can think of them as the whole thing as a function on the symplectic space, constant along this subspaces parallel to H minus, to fibers of cotangent bundle. And so in that sense, it's an element of the quantization space, element of the corresponding Fock space. However, there is a slight twist here, namely these FGs were formal functions in the variables, which is sequence, that time it was T0, T1, T2 sequence of vectors in the cohomology of the target space. And the point was that the Taylor coefficients of that series were the kind of the elementary Gromit invariants, some correlators that we wanted to encode in the generating function. But now we shift the origin. For some reason, we shift the origin to the point with minus v times z, and v in our real life is just as units, so minus 1 times z. 1 is a vector in cohomology, and so therefore, this is kind of a formal function in the neighborhood, not of the origin, but of this point, so this shifted point. And if you ask why are we doing that, let me look at take a look at this formula again, and point out that some interesting feature which no one actually understands properly. See that this is, I'm thinking of replacing this differentiation operators with so multiplication operators with kind of q's, and differentiation with p's. So it is kind of quadratic, it's quantization of quadratic Hamiltonian, what's written here. And it is, well, this part is homogeneous, right? It's degree 2. But there is one affine term, so this is degree 1 term, right? If it's there is just one differentiation, but look at it carefully. So it's a derivative in respect to T node. Node means that the coefficient in the basis in cohomology at 1. Phi node is 1, and index 12. It means that it's the T is a coefficient that well, psi to the power 12. Well, so so that this input in the correlators are such series T0, T1, Z, T2, Z square, etc. Where this T0, T1 is a homology classes. Therefore, that's corresponds to Z to the power 12. But But there is, in this sum, there is also the same derivative, namely if I take I equal to 1 and mu equal to 0, then the same differentiation appears there. Now, the coefficient here will be therefore T0 superscript 0 subscript 1. And if I shift that coordinate by -1, then I kind of consume that term. So this term can be added here if I shift the origin in that one variable by 1. And somehow mysteriously in all, all formulas that grow within theory, the kind of recursion relations, they all look like almost homogeneous, slightly inhomogeneous relations, will become exactly homogeneous if you make that same shift in all these formulas. That's exactly the same that you see here. And that's why it's kind of convenient to make all inhomogeneous formulas homogeneous. It's convenient to shift the origin to this point. And I don't think anyone really understands why it happens so, but that's a kind of effect of life. Okay, but so okay, so therefore we have this. Therefore, this generating function considered as an element of the Fock space, which is a quantization of the symplectic space. In genus 0, if we're concerned only with F naught, the genus 0 theory, then it means that we should take quasi-classical limit and then the symplectic geometric datum that corresponds to it, it's a graph of differential of the function f naught, which is a section of this cotangent bundle, or as a formal germ of a section near this dilaton shift. And so it will be denoted L. Therefore, if we consider with genus 0 theory, then we don't need quantization, just there is some germ of Lagrangian section which captures genus 0 invariance, and it is in that symplectic space. But if we are concerned with higher genus, then we need quantization. And now here is this kind of standard rules how to quantize quadratic Hamiltonians. So these are linear Hamiltonians. This is therefore if there are Darboux coordinates and some Darboux bases Q alpha and P alpha, then they are quantized into differentiation and multiplication operators this way. Respectively, the quadratic Hamiltonians are quantized this way. It's the multiplication divided by h bar, or second order differentiation multiplied by h bar, or if we quantize the product of Q alpha P beta, then here is a place we need to do some ordering decision, so that the decision is a differentiation first, multiplication after. But okay, so we have this quantization. It is not exactly a representation of the Lie algebra of quadratic Hamiltonians by differential operators. Namely, if you take you quantize this way two quadratic Hamiltonians f and g and compute the commutator of the corresponding operators, then it is the same, almost the same as taking the Poisson bracket of those Hamiltonians and quantizing that. But there could be some central extensions. There are some constant, some cocycle. Here a scalar cocycle, which is written here. It's actually, it is for Darboux monomials, it is 0 unless you have identical P and Q monomials, and it is either 1 or 2, depending on whether alpha is equal to beta or not equal to beta. But this more complicated formula, this P bar and Q bar, just take care of the fact that we live in super space, so that we should take into account Z2 gradings, and it's slightly different. So but anyway, there is some, it's really essentially, it's just when you commute second derivative across quadratic monomials, and some constants come out of this. So that's it. So now what turns out that that those differential, in these notations, these differential operators are simply the following thing, so that the operators are quantizations of monomials. That is, if you consider the space Laurent series multiplication by Z2L minus 1, this such multiplication, if you think of this symplectic structure, it's anti-symmetric with respect to the symplectic structure because the odd power, z raised to the odd power, because of this extra minus, it's actually anti-symmetric operator with respect to symplectic structure. Therefore, it is infinitesimal symplectic transformation. Therefore, it corresponds to some quadratic Hamiltonian, and you can quantize it. And this is what these operators delta L from that Faber-Penry formula are. So that's just multiplication by monomials. It shouldn't be too surprising if you look back at this formula and see that this is indices of differentiation multiplication are shifted by the same constant 12 minus 1. Therefore, it's kind of not surprising that in this notation it will just correspond to the kind of multiplication by a monomial, and the pattern of second derivatives actually kind of agrees with that rule. Okay, so we now have therefore very convenient language in which we can describe identities between generating functions, and at least in this case of Hodge integrals, the formula looks particularly simple. Any questions about this? Okay, once we have this language, this formalism in place, we can apply it in a more general situation, and that's what quantum Riemann-Roch theorem is about. Namely, let's examine this diagram first. So what is here? There is a modular space of stable maps with target X, degree D, genus G, and mark points compactified, and this is similar space with an extra mark point. The projection consists in forgetting that extra mark point, and we discussed this with you in more special situation, the Riemann spaces. The fiber over a point here, so a point is an equivalence class of stable maps from some curve sigma with mark points to X. But it has n mark points. But adding one more mark point is more or less like just it's picking a point on the curve, and so it's not surprising that the fiber here is the curve itself. And if you consider evaluation at the n plus first mark point, restricted to the fiber, it will be that very same stable map of the curve to X, whose equivalence class corresponds to the point on the base. So therefore, this diagram itself, this projection and evaluation with values in X, that's kind of universal stable map with this data, Gn and D. Now, the problem that was solved by Faber and Penry was take trivial bundle, one-dimensional trivial bundle over this space, pushing it forward, taking the Hodge bundle as an essential result of it, and computing its characteristic classes or bringing them into the intersection theory. But we can do more generally. I think we can take, say, some other bundle over that space. For example, we can take some complex vector bundle over the target, can pull it back by evaluation to that curve, and then push it forward in K-theoretic sense. That is, compute shift cohomology of that bundle over the curve. So in other words, it is some element of K-theory of that bottom space, which I do not here E, G, comma, N, comma, D. And it's kind of defined formally this way, but the meaning is for a curve sigma mapped by phi, map phi to X, you can pull back the bundle over X to the curve and compute H naught minus H1. So kind of the shift that's what corresponds to this element of K theory. And now you can therefore ask, so it's a more general situation than a trivial bundle. If it is trivial, then we are back to the Hodge classes. But now we can take characteristic classes of this new element of K theory and bring them into intersection theory. More formally, it's done this way. You pick S. What is S? S. So it's a universal invertible multiplicative characteristic class of complex vector bundles. So we discussed with you that Chen character is additive. Its components are universal additive characteristic classes. Therefore, this linear combination with arbitrary coefficients as k is the general additive characteristic class, and e to that is a multiplicative, and it's it's invertible because you put minus here, then you get the inverse class. So therefore, that's kind of general invertible multiplicative characteristic class of complex vector bundles, and you can apply it to that element, compute it on this element, and bring it into the intersection theory. Whenever you want to compute this correlator, you modify it. You twist this. TW stands for twisted. You define twisted Gromov invariance by systematically inserting this particular, well, it's a general characteristic class into the intersection theory. In other words, you replace the virtual fundamental cycle with a cap product with this characteristic class or this index bundle. And this way you get therefore new theory depending on the parameters as before, S0, S1, S2, etc. So there's a family of theories, and the problem is, can you express them in terms of untwisted, so in terms of old invariants? So again, you can form, as before, this total descendant potential generating function and consider it as an element of the Fock space of the corresponding in the symplectic formalism. There is a little certainty here, though. Namely, the Poincare pairing that defines the symplectic structure on that symplectic loop space, now it should be also twisted to be systematic. So you need to insert that that characteristic class of E into the integral over X, which defines the Poincare pairing. So therefore, therefore, for this deformed and undeformed theory, the loop space is the same as just Laurent series with coefficients in the cohomology of the target space. But the identity map on it is not symplectic anymore, because the symplectic structure depends on S. It varies with S. However, you can kind of modify. So if you consider not the identity map from H to itself, but so there's a Laurent series, and you can multiply by square root of this characteristic class, which is just multiplication in the class. So F is a Laurent series in Z whose coefficients are cohomology classes of the target, and you multiply each coefficient by that same cohomology class in the classical cohomology algebra. So this way you can redistribute that S of E is in between A and B as a square root, and then it becomes so it kind of equalizes the symplectic structure, if that's what you want to do. Therefore, that's this map multiplication makes a symplectic transformation from undeformed space to this deformed symplectic space, deformed symplectic structure. Anyway, so that here is the answer to that question: how to compute this twisted invariance in terms of untwisted ones. And this is the quantum Riemann-Roch theorem, and the answer looks this way. So so this bracket means that I'm thinking of D as a quantum states, a quantum state in the quantization space. It means that it's a not function up to a constant factor, non-vanishing constant factor. So it's one-dimensional space spanned by this. It means that in this formula I'm omitting some normalizing constant that can be computed also explicitly. It's computed now paper, just don't want to bring it in now. And so therefore this twisted total descendant potential is obtained from untwisted one by exponential of some quantized quadratic Hamiltonian, which depends on these parameters S1, Sk. So it's similar to what was in that Hodge class story. And what will remain is just to describe what is this. So what exactly is this operator? What is a quadratic Hamiltonian? And the statement that it is, that was written here, it's Euler-Maclaurin asymptotics of this infinite product. So what is it here? So S is that my multiplicative, invertible multiplicative characteristic class. It's applied not only to E, but E is tensored with minus m tensor power of a line bundle. Which line bundle? It's line bundle whose it's a bit cryptic. I'll explain in a minute what it means in reality, but it's suggestive expression. So it's a line bundle whose first-chain class is Z. So Z is just a letter here. It doesn't mean anything. But if you recall that story with, as I already recalled it today, of S1 equivariant Floer theory in the loop space, Z was the generator in the cohomology of CP infinity of the equivariant theory with respect to coefficient ring of the equivariant theory with respect to circle action. So therefore, that L is the hyperplane line bundle over CP infinity, and Z is the first-chain class of it. But so what is this Euler-Maclaurin asymptotics of this expression? Here is explanation of it. So first of all, let's take the logarithm of this infinite product. Therefore, I assume that that capital S is exponential of some lowercase s. Lowercase s is so that if E were a line bundle with a first-chain class X, then that expression. This expression, right, where that's the logarithm I'm talking about. So it's a general linear combination of what x to k divided by k factorials components of the Chern character of one-dimensional bundle, and therefore that exponent would be this expression. So there is a thing of a series or function of x or some series in x with arbitrary coefficient sk. Now. What is written here then, it means that I shift x by, well, subtract m times z. So I don't need to know what the topological meaning of this. So that this expression means that just I take that function and that series and shift the variable by mz, minus mz. And sum from m from 0 to infinity. That's what logarithm of this expression actually means. If E is a vector bundle, it means that not line bundle, then as usual, so by the splitting principle, you can think of it as a sum of line bundles, and it will be not one x, but several x's. Xi is Chern roots of it. You sum over this over i's also, and express everything in terms of symmetric functions of x's and substitute in the Chern classes of E for them. But that's kind of it's relevant for the moment. So let's consider this is the case on 1x is there. So it is sort of classical problem that was answered by Euler and Maclaurin. You see that this is finite difference integral, right? So there is a function s of x, and this integral from 0 to minus infinity with a small z is a small step of finite difference integration. And the question is how to express this in terms of ordinary integration, how this finite difference integration is related to ordinary integration. And here is a formal procedure that give the answer in the asymptotical limit when z tends to 0. The step of integration tends to 0. So first of all, you interpret this translation. Translation is exponentiation of differentiation, right? Therefore, if you apply to function s of x e to minus mz d over dx, it formally means that by Taylor's formula that that x is shifted by minus mz. Okay, so now you need, therefore you have this sum. What is written here is sort of a geometric series, right? You take e to minus z over dx and take the sum of its powers. Therefore, it can be formally summed into the sum of geometric series, 1 divided by 1 minus that translation operator. The problem with this green expression is that it has z small, and therefore you kind of have a 0 in the denominator. You cannot divide by 0, as everyone knows. So what you can do, therefore, you need to offset that 0 by multiplying by this differentiation, by dividing by this differentiation. When you divide by differentiation, it means that you're actually integrating. Therefore, you take antiderivative of s divided by z, and then apply these things. But this thing already, it's a familiar Todd series, which if you expand it with respect to the derivative, it will spit out Bernoulli numbers, and that's what you get. Therefore, this is the final asymptotical expression. You see that the first term is just antiderivative of S divided by Z. You can anti-differentiate each monomial. The next term is the only one in that Todd series which is not even. It gives you 1/2 of S divided by 2, just S of X divided by 2. The rest is, you see that there is 2L minus first derivative. It's what is left from that series expansion, multiplied by Z to 2L minus 1, and there is a Bernoulli coefficient here with factorials. So now so the point is that this is really what that delta operator is. So delta is the operator of multiplication in the loop space. Applying this operator, let's stare at it a little bit. This term, when you take the exponentials, it's exactly multiplication by square root of capital S of X. That's this term. Therefore, it equalizes the symplectic forms like here. That's what it does. But the rest of the terms are actually infinitesimal. They're anti-symmetric with respect to our symplectic structure. Because these are multiplication by Z to the odd power, we already encountered them, and this is also 1 over Z. It's an odd power, means that they're anti-symmetric. And what comes from here, it is, you write explicitly, so okay, you differentiate the series, but there are multiplications by components of Chern character of your bundle E. Their multiplication cohomology algebra with the Tarski space are symmetric with respect to the Poincare pairing, and therefore the whole thing is anti-symmetric. And anti-symmetric means that it's infinitesimal symplectic transformations correspond to quadratic Hamiltonian. You can write down the quadratic Hamiltonian, quantize it, and take the exponentials. That's what this formula means. So that without that term is symplectic, but this term it transforms one symplectic structure into the correct one. Of course, so you see that in this formulation, the Bernoulli numbers on the right arise from this Euler-Maclaurin asymptotical procedure. In the proof of the theorem, of course, they arise from the application of Grothendieck Riemann-Roch formula, because what we do, we kind of have a generating function with this S's inserted, we differentiate. The proof is infinitesimal. We differentiate in Sk. It brings down here some components of Chern character of this Hodge bundle, of this, not Hodge, this index bundle. It's integral over that space. You express it by Grothendieck Riemann-Roch formula as push forward of something from the top space, and it means that you can, instead of integrating something that you poorly understand, this Chern components of Chern character, in this space you can integrate over the upper space something that you understand very well, which goes back to the invariance that we already know, and that if you analyze it, it becomes some differential, second order differential operator, and that operator turns out to be exactly the quantization of this expression. So that it's kind of also suggestive that this expression is a asymptotical expression of this infinite product, which, in a minute will remind it of something already familiar. Any questions? So that's the formulation of the title theorem of this lecture series, of this quantum Riemann-Roch theorem. That's what it is. For my exposition, it's an intermediate point in the story, but still, that's what theorem is. So it allows you to compute this, at least tells you how twisted invariants are expressed in terms of the untwisted ones. No questions? Okay, let's now consider a special case. Let's try to apply it to some useful situation. As I told you last time, at some point, Maxim Kontsevich told me that he was trying to use some Riemann-Roch formula in order to prove the mirror conjecture, or something for quintic threefolds or something like that. And I said that I totally couldn't understand what he was talking about. Now let's see what he was talking about, because now we can understand it. Suppose that there is a situation, so that there is some space X, for instance, a complex projective space, and Y is some hypersurface, or maybe zero locus of a section of some holomorphic vector bundle over it. For example, CP4, and Y is a quintic threefold, which is a section of degree 5 line bundle over X. Then well, in any case, if there is Y is subspace in X, then the moduli space of stable maps to Y, well, it's mapped, it's included into moduli space of stable maps to X. This is true in high genus as well, but it turns out that in genus 0, you can express the virtual fundamental class of that space as in terms of the virtual fundamental class of this space. Namely, it is the product of the virtual fundamental class of this space, kept product with the earlier class of the appropriate bundle. So let's see why. So let's suppose that you have, so the Y is a section, is a zero locus of some section S of bundle E, right? So suppose that there is some stable map, there is some holomorphic curve sigma mapped by some holomorphic map phi to X. Now you can restrict that section to the curve or compose it with phi if you wish, and then it becomes a global section over the sigma over the curve of pullback of that bundle to by phi to the sigma, right? So therefore it's an element of H naught, zero cohomology of the curve with respect with coefficients in that induced bundle, induced by a stable map. So therefore, if you think of it for all sigma, there is this moduli space of stable maps. Then for each point, there is such a map, and therefore for each point in it, there is this zero-dimensional cohomology space, global sections of the bundle E pulled back to the curve, and there is a vector, this vector, in the restriction of the section to that curve in that cohomology space. In other words, you have that S induces a section, not that S hat here, a section of that index bundle, that E0 and D, which consists of H naught minus H1. It's especially true if H1 isn't there, but even if it is there, still there is some section of this shift, which might be of H naught, which might change the dimension from point to point, but still there is such a global section. So it turns out that this space itself is sitting in the ambient moduli space can be something bad, can have components of wrong dimension, have singularities, whatever. It means that the section S hat is not transverse to the zero section, but nevertheless, the virtual fundamental cycle in it is exactly what it would be if this section S hat were transverse to the zero section, and therefore it means that the virtual fundamental class is the Euler class of this index bundle E0 and G, so it's H naught minus H1. So apparently that's what Maxim tried to do. He was trying to so that earlier class, it's a characteristic class of some index bundle. It should be in principle computable or expressible in terms of using Riemann-Roch formula, and he was trying to apparently compute invariance of, say, quintic threefolds in terms of ambience, known ambient invariance of the projective space using Riemann-Roch formula, probably something like that. Now we are in a position to do that. We have this general formula. There is one sentence. So the Euler class is a multiplicative characteristic class of vector bundles, but it's not invertible. It's rather nilpotent, right? So you need to, therefore, to apply that machinery of quantum Riemann-Roch theorem, you need to perturb it a little bit. So namely, what you need to do is the following. So consider so we have a vector bundle E over a target space, complex vector, homomorphic vector bundle. But let's introduce a circle action or C star action there fiber-wise. It doesn't act on the base on X, but it just multiplies by scalars on the fiber. And let's consider equivariant theory with respect to the circle action, this T1, it's one-dimensional torus action. The coefficient of that equivariant theory, it is polynomial algebra in some generator lambda. So it's cohomology of CP infinity, and lambda is a generator and cohomology of the CP infinity. Then the equivariant Euler class. So if your bundle has Chern classes C1, etc., CD in dimension D, then the equivariant Euler class is this polynomial expression. So in terms of Chern roots, it is this product. So when lambda is 0, it is Euler class. It's product of x1, xd. But the equivariant Euler class is such an expression. And because in principle you allow division by lambda in terms of localization, fixed point localization, you kind of allow to work over a field of rational functions over lambda, field of fractions of this ring. Then this expression is invertible. Xi's are nilpotents, but lambda is something invertible, and so it's okay to divide by that whole thing. So now I'm interested in genus 0 now because this relation between virtual fundamental cycles, it doesn't hold in high genus. So there are some complications, and it holds also only in genus 0 in this case. But in genus 0, therefore, what we have is there is as I told you that genus 0, it means that there is a graph of differential of the generating function for genus 0 invariance, which I denoted this curly L. And it is Lagrangian section of the Lagrangian submanifold, formal germ of Lagrangian submanifold in my symplectic loop space. Let me show where I mentioned it. I did mention it somewhere. Yeah, it's here, right? So that's what I'm talking about. But now there is the one which corresponds to the theory on X, and the other one which corresponds to doing what? To systematically inserting in my intersection theory this equivariant, S1 equivariant Euler class of that index bundle. The notation for this new theory twisted by this equivariant Euler class is pi e. The explanation for the notation is the following. So it's not, first of all, it's not exactly what we are doing here by interpreting invariance of y in terms of x. It's not exactly the invariance of y in particular, because you can do intersection indices only with classes which are pulled back from x, which might be not everything, but nevertheless, it captures something about y. But let's distinguish the theory, the Gromit invariance of y and of this twisted model, twisted by this Euler class. That's why a different name. Pi e pi is its parity, it's a function of parity change. Namely, I'm thinking of this e whereas of total space of the bundle is a superspace. Therefore, X is even space and the fibers are odd. And the reason is that the dimension of a supermanifold is the difference of dimensions of even and odd part, and will be exactly the dimension of Y. And so therefore, let's think therefore that we are computing and growing invariance of a supermanifold pi E, where it's a, so that where E is odd bundle over X. Anyway, therefore, the quantum Riemann-Roch theorem in this genus zero version tells us that there is this cone of this new theory and this this Lagrangian section of that new theory, Lagrangian section of the original theory, and they are related by not quantized, but by that symplectic transformation that was in the previous page denoted by delta, and here I'm denoting it by the square. And so what is the square? It is Euler-Maclaurin asymptotics of, well, that's what I should write. So my, so Euler, if that's my Euler class, then that's what that class S. And then that's what that infinite product should look like. If E is a line bundle, there is only one X, and we can forget this green product and summation, just there is this infinite product. So once again, therefore, that I should take this infinite product, process it through this Euler-Maclaurin asymptotical procedure, and that's what we'll actually get. It is one thing that you can see here is that you can see that indeed the relation does make sense for lambda equal to 0, because the formula contains this nilpotent in denominators. But if it's if lambda is non-zero, they can interpret it as the sum of geometric series in x divided by lambda, then it's fine. Also, this is exactly the modulo some slight change of notation. It's a famous asymptotic of the gamma function. Stirling's asymptotic of gamma function when the variable tends to infinity. And this time this d tends to 0. And it's not surprising, because this infinite product is this kind of gamma function, right? So if you shift the variable x by z, then there is some kind of it's more or less the same product, except that one factor comes out of it. So we already encountered what is remarkable, that we already encountered this expression when we're doing that heuristic analysis of S1 equivariant Floor theory on the loop space. We see that this is, so if LP is the first-Chern class of my line bundle, so therefore I have, in that case, in the projective space, we had hypersurface of degree L, and LP would be, P is a hyperplane class, LP would be the first-Chern class of that degree L line bundle, and this infinite product, that's the class that we were using last time, and we came up with what? We actually found hypergeometric functions which are related to the genuine invariance of the hypersurface by they have something to do with it, maybe not literally equal to it, but to the invariance, but related by some mirror transformation, at least according to the mirror conjecture. That was the story. And so that time looked remarkable, that we found hypergeometric functions on the same side of the mirror, not where they originally appeared as some integrals, some periods of mirror manifolds, but rather on the B side. But on the A side, where we think of Floor theory, holomorphic curves, etc. So now we have that same gamma function, or at least it's Euler-Maclaurin asymptotics. We have it in the genuine Gromb-Witten theory, and it came up with applying, when we applied the quantum Riemann-Roch formula in genus 0 to to the Euler class. So that should make us very happy, because it seems that we're very close to proving, so to making that rigorous, that heuristic picture rigorous, and actually understanding how what Maxim didn't manage to do apparently at that time, to figure out how to prove various mirror formulas using this quantum Riemann-Roch theory. And so that's what we tried to do with Tom Coates at that moment. So we're very happy that we're very close to the goal. And somehow didn't quite work. So that it's even though there is this, so I said lambda equal to 0, it is exactly that expression that we had there. And this thing that okay, so we already know that these two things are related by not by this product, but it's asymptotical expansion, and some mirror formula should come, hypergeometric function should come out of this, and but somehow it's not clear why and how, so absolutely unclear. So that then understanding comes that maybe it's not enough to know how these two things are related. They're related by this transformation, but maybe you need also to take into account the properties of Gromov-Witten invariance of genus 0. That is some identity, some properties of this this Lagrangian section. So therefore, there are in Gromov-Witten theory there are lots of identities, universal identities between Gromov-Witten invariants, which kind of come from the fact that Deligne-Mumford, the various strata in Deligne-Mumford space, especially in genus 0, well, they represent, different strata may represent the same homology classes, and that generates some universal identities between Gromov-Witten invariants. And maybe it's not enough to know how things are related. You need to also involve all the intrinsic identities in, which constrain the properties of this L and that L. And that's what we need to do next. And these identities involve what's called the string equation, the Dilaton equation, infinitely many what's called topological recursion relation, which are some infinite system of third order partial differential equations on that function f naught of 0, that the generating function for the standard differentials. And eventually it turns out that we need also the divisor equation, but we will not talk about them today. But today, well, after the break, we will talk about this identities, universal identities for Gromov-Witten invariants. Thank you. So, they said we need to discuss some general identities satisfied by Gromov-Witten invariants, the string equation, the Latam equation, and actually what's called ancestor descendant correspondence. In genus 0 theory, in fact, the string and the Latam equation they follow from descendant ancestor correspondence, but nevertheless, let me mention them separately. So the geometry topology behind is very simple. So suppose that you take class 1 on that space and push it forward in homological sense, integrate over the fibers, because you get 0, say for dimensional reasons. When you push forward, degree should become smaller by the dimension of the fibers, so it should be -2, but there is nothing in the degree, so it is 0. Likewise, if you take the psi class, the first chain class of the cotangent bundle, of the bundle defined by the cotangent space at the current mark point along the fibers and plus first mark point, then the push forward of it in homology theory should be constant, should be degree 0 class. But it's easy to see that what's constant, it should be minus the Euler characteristic of the curve with punctured at the end mark point, so that it's 2g minus 2 plus m. The fact that you can ask this question, what will happen if I consider this correlator involving this 1 or this psi, but you know the answer a priori, means that it imposes some identities on generating functions, some constraint on generating functions, and that's how they look like. This string equation that comes from this looks like such a yeah, such a differential equation also looks like quantization of some quadratic Hamiltonian. This time there are a derivative of first order differentiation multiplication, so it's quadratic terms. There is no second differentiation, rather there is a multiplication by a quadratic function. That's Poincare pairing. Just break it. But it turns out that in our formalism, what this differential equation expresses is very simple. It is just that if you take that total descendant potential and apply the separator quantization of 1 over z, so division by z, in that loop space, it gives you from quadratic Hamiltonian, which is behind this formula quantized, so the result should be 0. Also, it is after the Latam shift. You can see here that there is some inhomogeneous term here. It really is meaning is that in generating function to bring in this one in one of the seats of the correlator, you need to differentiate in this variable t naught naught, and then you kind of compute the yeah, so that the effect of it on generating functions. But point is again, so if you shift. If you take mu equal to 0 and k equal to 1, then this will be exactly that derivative which is here, which means that if you shift that variable by 1, that t0, 0, then this term will be included. Then that's again, that same Latam shift makes this formula homogeneous, and then this is the string equation in our concise formalism. The Latam equation leads to this equation, which actually this is the Euler field with respect to all the variables, except that again it's better to Latam shift one of them to include that term. But then it essentially means that fg, the genus G potential, is homogeneous function of degree 2 minus 2g. And for genus 0, it's therefore that f naught is homogeneous of degree 2, but after the Latam shift. Therefore, it's when you shift the origin in one of the variable by 1, then it becomes homogeneous function of degree 2 in genus 0. In genus 1, there is some anomaly, and I think I made a typo. It should be the Euler characteristic of the target space here divided by 24, and it comes from the fact that in degree 0 in genus 1, there are no curves. There is no moduli space with no mark points, and so that kind of, there is some terms that you can compute, have to compute by hand or something like that. So there's some anomaly that comes from that. But anyway, so there are such identities, but the most important thing is the following story, namely. So what's here? So that let's consider this moduli space of stable maps to X of degree G, genus G, and n plus L mark points. I can forget so therefore a point here is represented by some map of curve, holomorphic, of some curve to X, holomorphic map to X. With n plus L mark points. Now, I can forget the map itself and try to remember the complex structure on the curve itself, only the complex structure, including the mark points, except that I also forget the first L mark points. Therefore, I can forget the map, forget the first L mark points, and remember the complex structure and remaining mark points, and typically it will represent that curve will represent some point in the Deligne-Mumford space MG and bar, and I can try to define this map. The station is a bit more complicated because, as we'll see in a minute, the curve, when I forget the map, the curve can be, and mark points, the curve can become unstable in the Deligne-Mumford sense, but then it means that I should contract, kind of remove the unstable components, and still I can determine the point in this target, determine which the remaining curve and the components need to be contracted, are contracted, so what that the curve is stable, the Deligne-Mumford curve, and there is such a map within these spaces. It's called a contraction map. Now, when I define Gromov-Witten invariance, I can do the following. So instead of psi classes that naturally live on this space, I can take psi classes, or it's Furtian classes of lines defined by cotangent line bundles over this space defined by cotangent lines at the mark points, and pull them back by contraction map there. And these classes I denote psi bars. Instead of psi 1, psi n plus L, I have this psi 1 bar, psi n bar. And similarly looking classes that come from the Riemann spaces. And I can incorporate them into generating function of my intersection theory. Namely, that's the kind of generating function I consider. It's a sum as usual over the degrees and these numbers of n and l mark points. In the first L mark points, I put just classes which are the primary class, no psi classes, no descendant classes, just pull back by evaluation maps homology classes from the target. It's just my choice. I could use psi classes, but I just don't need them. But in the remaining endpoints, I put the usual expressions, T0 plus T1 psi plus T2 psi square, etc. Except that instead of psi classes, I take psi bar classes. Which are kind of similar, close to so the line bundles which come from this space and they live in this space. They are not too foreign to each other, but still not exactly the same. And so this way, therefore, I get new generating functions which are called ancestor. They call this, therefore, these classes ancestor classes, and rather than descendant classes. And this is ancestor potential, gene ancestor potential. It depends on tau as a parameter. So there is a family of them. So therefore, and altogether, if I combine all genera, I can form this total ancestor potential. This bar indicates that I'm using this new generating functions. And everything, this A depends on the tau as a parameter. And the question is how to, can we indeed express this invariance in terms of the descendant potential? So how are they related? In fact, historically, the story is like that. Probably many people knew the geometry, how these psi and psi bars are related. But Getzler was the first one who wrote something about it, and his kind of very important point was that that some simple identities between psi bar classes in the Riemann spaces, they generate very non-trivial relations between Gromov-Witten invariants. And even simple ones, when you just take some monomials in psi bars, which are zero for dimensional reasons, because they just degree exceeds the degree of the dimension of space. Even that translates in some non-trivial universal identities for Gromov-Witten invariants, and that's how his idea was. That's how what people call topological recursion relations. That's how they come about. Then Kantsevich and Manin, perhaps independently of Getzler, explored the situation, and they said that, well, these ancestor potentials are related to descendant potentials in each genus by some linear transformations of this T variable. So that they wrote some simple linear transformation. And then we, with Tom Coates, added kind of a cherry on the cake by showing that if you combine these linear transformations all together and take into account various special circumstances, such as various anomalies, the dilaton shifts, that's something that special that happens in genus 0, then and in genus 1, then actually you get very neat quantum formula in our formalism that relates this descendant and ancestral potential, and that's the formula. So here is that element of the Fock space that represents descendant invariance. This is a family of elements of the Fock space that represents the ancestral potentials, depending on tau. So this is, you need to put this function by hands. What is it? So it's, I see that in genus 1, you can consider for positive degrees, you can consider elliptic curves in X with no mark points. There are such moduli spaces, and there are some with no mark points. No, this n is 0, and there is just a primary invariant with no descendants or ancestors, and that's what this generating function is about from genus 1. But in ancestor, so it's present in descendant side, but there is nothing in ancestor side because there is no that M0 M1 genus 1's no mark points bar is not defined. There is no such space. It starts with for genus 1, you need to have at least one mark point to make it stable. And so you need to add this term by hand, but when you do that at some function of tau, then it is a result of application of some quantized transformation to D. And that quantized transformation is written here, but let's look at the geometry first. Just let's see why this psi's and psi's bar are not the same thing. So here is a picture. So this is a codimension 1 phenomenon that happens in the moduli space, in this moduli space in some device, in codimension 1. And so suppose this is mark point on which some psi cluster for this green line, it's a cotangent line to the curve at that mark point, and psi is a first-chain class of lines, that line bundle formed by such points. But imagine that your curve, so if your curve is sort of irreducible of genus G, then that line, if you forget the map to X, and then still your curve will be a stable curve, and psi bar will be first-chain class of line bundle with the fiber is the same. But imagine that your curve degenerates into the following thing. There is some curve of genus G plus rational component CP1 attached to it, on which there is this point where you take that psi class, and maybe this pink point is carrying the classes tau, but no mark points from the second set, from this L plus 1 to L plus n with these numbers. Then when you forget, so that the map to X is stable because the map on this component is non-constant. It carries so it's, for example, for that reason. But then when you forget that map to X and forget this pink mark points, then it is a rational component that carries only two special points, this mark point and the node. And it's unstable in the Riemann-Roch space. It has, you can rotate around these 2 points. So therefore, what you need to do, the corresponding curve in MGN will be by just contracting, removing that component, and placing that mark points onto the place where this node was located to this curve. And so that will be the curve which represents the complex structure represents a point in the Riemann-Roch space. But now we see that therefore the line which is a fiber of that line bundle whose first-chain class is psi bar is now this line. So it is not that line but this line, and therefore these two classes psi and psi bar, they differ by therefore by this divisor of the hypersurface and this modular space where this phenomenon occurs. And if you systematically take into account these differences, then it leads to this formula. Namely, what is this S? It is the generating function for invariance which exactly captures this phenomenon itself, so that it you see that there is what is it? So with correlators which are there, they're the following. There are L plus 2 mark points. At L mark points, there could be this class is tau, like these pink points. But in addition, there are 2 more mark points. One is this one, which carries just some class psi, some basis class phi alpha, which is it's a matrix, right? So it's one of the indices of the matrix. The other component carries whatever expression you want. So this is general, so some expression involving this psi classes that one comes here. Therefore, if you just look at this correcting terms, which makes difference between this curve and that curve, then the invariance which Gromit invariants which correspond to such curves are captured by this generating function. So it is genus 0, L plus 2 mark points, and no descendant classes except for this one mark point. Yeah, so therefore this is some if you can think of it as 1 over z series, because psi is nilpotent, you can expand it as 1 over z series, geometric series, and so it belongs to genus 0. In fact, as an object itself, it is okay. It's an element of the loop group in our loop space. So it is a matrix which acts on cohomology space, as the string indices indicate, and it is a series in 1 over z, so that it is therefore an element of the loop group of our symplectic loop space. And moreover, it turns out that it satisfies this identity, that if you take the transpose with respect to Poincare pairing of that matrix and put minus z there and multiply with it itself, then you get identity matrix. That identity exactly means that S is a symplectic transformation on our symplectic loop space. And so therefore it defines some transformation through quantization on our Fock space. That you take its logarithm, it becomes an infinitesimal symplectic transformation, and it corresponds to quadratic Hamiltonian. You quantize it and take the exponential, and that's what this as tau hat means. And this is the relationship. So that's between descendants and ancestors. If you have questions about this, please ask, because we will now go to extracting consequences of that for genus 0 Gromit invariants, namely in geometric form of that Lagrangian section, which is a graph of differential of the function f naught. No questions. Okay. Okay, so first of all, what is, so again, there is this loop space. It's a Lorentz series in Z with coefficients in the vector coefficients in cohomology. With the target space, it's equipped with a symplectic form, and there is Lagrangian. So there is this in this picture, H plus, it's a power series part of it. This H minus, it is principal part of Lorentz series. And there is a pointed dilaton shift. And somewhere over that point, there is formal germ of a Lagrangian submanifold, which is a graph of differential of the genus 0 potential with a shifted origin, right? Now, what it is explicitly, if you do compute the first derivative of the generating function and assemble them into point in the Lorentz series, and how it will look like. So it's the point. There, first of all, it's kind of it's a 2-point projection. It's a graph, right? So there is a projection here, which is the input, and a projection in that direction, which is the answer, the invariants themselves. So the projection in this direction, it is, first of all, there is this -1 times z, it's a dilaton shift, plus some power series in z, which determines the equations we ask. So that's it's something that determines what we put in the input into each mark point in our generating function. And the projection in this direction, that's the generating function of consisting of invariants. It is, so this, okay, so what is it? It's a alpha is the index, it's a vector function, it takes values with cohomology. Phi alpha is the basis in cohomology, so it's the summation over alpha, it's components of that vector. There is number of mark points and the degree, Q2D divided by n factorial. So this expression, so that phi upper alpha, it's just Poincare dual basis. Here there is summation over alpha here. And this expression is means that this is such a geometric series, which shouldn't surprise you, so that together with this phi alpha, each such a term and this expression, it is exactly one partial derivative of the genus zero potential. So if you like, let's go back to just recall our notations. Yeah, so that's the Darboux coordinates, right? So if do you see that that what is the graph of differential? It means that you should equate this p, the coefficients and negative powers of z, to partial derivatives of the generating function of this kind of generating function, partial derivative with respect to the corresponding variable t. So here, so that's exactly what you get. So in one place you will have this particular monomial. It's exactly the partial derivative in the direction of this psi k, and there is minus 1 over z to k plus 1 the denominator. So if you compare that, that's a graph of that's how the graph of differential looks like. So that explicitly, and the name for it is a big J function. Therefore, it's to each. It's kind of parameterized by this space for each point here. T, you have this. You lift it to a point in that Lagrangian section, and that's what it is. Now, the main point is that if you apply the descendant ancestor correspondence, that is in genus zero, therefore you need to apply that symplectic transformation S that was given by this matrix, right? Apply to get the similar, so the graph of differential of the genus zero ancestor function. So that's how this therefore this the Lagrangian section corresponding to descendant theory, you apply that symplectic transformation and you get the section corresponding to the ancestor. If the bar indicates ancestor, and there is a parameter tau. But there is the following phenomenon now, that this Lagrangian section actually is tangent to H plus along Z times H plus. So it's tangent to the space of power series along a subspace which is power series with zero free term. And here is the reason. See that the Lie-Mumford space of genus zero with n plus 2 mark points has dimension, complex dimension n minus 1. So it's number of mark points minus 3, right? So it's because SL2C, the three-dimensional groups of transformation section on CP1 and moves points around. Therefore, if you have some correlator where well, could be anything in 2 mark points, but in the remaining n mark points, there are some classes in psi bar, which are with zero free terms, therefore they're divisible by psi bar. Then the degree of this integrand, when you multiply them, it's already n, it's complex dimension n, so real dimension 2n, it exceeds the dimension of the manifold, and therefore this must be 0. It means that the that ancestor function f naught bar, if you it's not only it vanishes when you evaluate it at the points where the input t of psi bar has 0 free term. Its first derivatives are 0 and second derivatives are 0, and it starts with cubical terms only, which means that, well, the value doesn't matter when you compute the differential of a function, but the fact that the derivatives vanish, it means that Lagrangian section intersects 0 sections at those points, therefore it contains ZH plus. But the fact that quadratic terms vanish, it means that it's a tangent. So it therefore along ZH plus, its tangent to its tangent space is H plus itself. So therefore, yes, for each tau, it is tangent to H plus along ZH plus. Now, now imagine what it means when I apply, take that thing and apply S inverse to it. So it tells me something about this cone L. It tells me that when I apply that S inverse, then there is this space here, ZH plus, and it's mapped to some subspace into into L, and along that subspace, the tangent space to that graph is the image of H plus. So, and when tau varies, actually, you can see that it gives me all, it applies to all points in that Lagrangian section. So the conclusion is the following. So that's the following theorem, which kind of is a geometric interpretation of all these identities, universal identities of genus zero growing within theory. It says the following, that Lagrangian section, Lagrangian submanifold, the graph of differential of generating function, is actually that's what it's, so that's a formulation. Let's read it. So L is an overruled Lagrangian cone. Namely, this means that the tangent space at any point f to that cone is tangent to that cone along z times that tangent space. So this is very loaded phrase. Let me decode it for you. First of all, it says that that formal germ of Lagrangian section that lives over this Dilaton shifted point, in fact, if you kind of analytically extend it, it is a cone. It is a cone with vertex in the origin. That, if you wish, is a consequence of the Dilaton equation, because according to the Dilaton equation, f node, Dilaton shifted function f node, is homogeneous of degree 2. It means that its derivatives will be homogeneous of degree 1, and that it means that the graph of differential will be actually a cone. Now, a cone is something that is ruled by lines, right? It consists of rays. But the claim is that this particular cone is overruled. So it means that it consists of infinite dimensional subspaces varying in finite parametric family. And it is as images by S inverse of ZH plus. But so this formulation itself means the following. First of all, that if you take a tangent space to this cone at any point, then it's invariant with respect to multiplication by z. So zt is a subset in it, which means that it's not an arbitrary semi-infinite subspace in the loop space, but it belongs to the loop space loop group Grassmannian. So the infinite dimension Grassmannian of the loop group. It's invariant with respect to multiplication by z. It comes from the fact that that H plus is invariant with respect to multiplication by z. And S inverse is from loop group, it commutes with multiplication by z. So that's this property. The second thing is what this phrase says, that if you take tangent space and multiply it by z, then the space will lie in the cone. It's because this ZH plus lies in the ancestor cone. Therefore, that after the S inverse, it will lie in the cone. So the cone is ruled by such infinite dimensional spaces, varying in finite parametric family parameterized by tau. So it's almost linear space, but it's curved in finitely many directions. And the second thing is that if you take in that for one tangent space, take z times tangent space, consider any point in that ruling space, then the tangent space to the cone will be that same tangent space t. So take t, then it is a tangent space to the cone at all points of z times t. It's again because that's true for the ancestor potential and H plus and ZH plus. So therefore, it's very kind of rigid constraint structure. Sergei Barannikov calls it semi-infinite variation of Hodge structures. It is so he was thinking in such terms, so that imagine there is some space T which varies in finite parametric family parameterized by tau, and it contains Z, t, z squared t, etc., and it's contained in the inverse t, the minus second t. There is this flag. And it varies with tau, but it varies in such a way that each next space infinitesimally varies inside the previous one. So it is Griffith's, it's called transversality condition. I would call it integrability condition. But so it is what the condition in the Hodge structures. So it calls semi-infinite variation of Hodge structures. So now, again, maybe appealing to one observation of the construction of Barannikov, let's discuss what people call the small j function. The small j function, it is as a formula, it is the same expression, except that you put only primary classes here. Just forget size. That is, it is this expression. It's minus 1 times z dilaton shift plus tau. It is just a cohomology class of the target space. And then you write that same expression, except that you put only this tau there. So in other words, it is the following thing. So that cone, it kind of remembers all this. It's a graph of differential of full descendant genus zero descendant potential, which is a function of infinitely many variables. But you take this, it's a function of this h plus around this shifted origin minus 1 times z. And now this is the h plus, but if you take this transversal direction, it means that you to minus z, you get just tau, you add three terms in the power series, but don't take any terms with z there. Then you get a function of finite many variables that is kind of the slice of that cone parallel to this h minus space. So you get kind of the over this. It's a line on my picture. It's finite dimensional space, isomorphic to homology of the target, and you take space parallel to h minus along it and intersect this cone. So you get some finite parametric family of points, but it actually determines this whole cone. Because it's if you compute its derivative, so that's how it looks. But if you compute the derivative, tau is tau. Tau is the sum of phi alpha tau alpha, right? So we differentiate in tau alpha, you'll get that's one of the components of tau. You get this disappears under differentiation, it's constant. You'll get phi alpha plus some 1 over z series here. And for if you do this for all alpha for a basis, you get actually basis in the tangent space. It's a basis in the tangent space at the pink point, where you at the point J, to the whole cone, but the basis over the ring of power series in Z. So if you, the tangent space, it's a module over this power series in Z, and so that's the basis of that module. Therefore, now if you multiply it by z, you'll get basis in the ruling space, and if you start moving parameter tau around, you kind of sweep the whole cone this way. But then what he says, let's do the following. So let's differentiate that basis in the tangent space. If you wish, these are rows of that matrix S, in fact. So that we'll see that this matrix S, it is. It consists of second derivatives of, and it is, so this J is sort of the first row of it, and if you differentiate it further, it gets this basis, the rows of that matrix S. Now, if you multiply it by Z, you'll get a vector in the ruling space. Now, if you differentiate it again, then you get again vector in the tangent space. But vector in the tangent space should be expressible in terms of basis in tangent space with coefficients which, well, they depend on tau as everything here, but they could be, a priori could be power series in Z, because it's a basis over this as a module over power series in Z. But in fact, if you think what you have on the left-hand side, so you differentiate it this expression in, once again, this term disappears. This is 1 over z series. You multiply by z, you get no positive degree terms in z. It starts from 0 maybe in negative terms. And this contains also only negative terms. But this, if it contained any positive terms, then the result would contain some positive terms. Therefore, the conclusion is that matrices actually cannot depend on z at all. So what you have here is therefore that this vectors, this matrix formed by this vector, so therefore it's, as I said, the rows of that matrix S. That matrix S is a fundamental solution to the system of differential equations, z d beta, some matrix applied to that vector. So it is therefore that matrix S is the fundamental solution to this connection, this actually one parametric family of connections. Parameter is z, and it's called Dubrovin's connection. It's if you know what Frobenius structures are, it's kind of the main ingredient there. And the fact that this connection has a fundamental solution means that it's flat. And flat means that the square of the separator is 0. It means that, in particular, it implies that the matrices A beta, this matrix commute. And these are matrices of quantum multiplication. That's what quantum multiplication algebra is. So for each tau, you have this quantum multiplication formed by this operator. So that the two vector phi beta that correspond to matrix, and this matrix is commute. But in addition, they also satisfy some, they also kind of partial derivatives of some other function. So that, but anyways, therefore that's what quantum homology algebra is, and therefore that's what the role of the small j function, and that's why yeah, so that it's important because it determines in a canonical way. It's kind of canonical slice of this overruled Lagrangian cone, which remembers the whole picture altogether. Okay. Any questions about this? So you see that what the situation is, we proved this, we'll establish this, formulated this quantum Riemann-Roch theorem, and in the case of earlier classes, found how the theories that we want to know for, say, hypersurface or complete intersection in the ambient space is related to Gromit invariant genus 0 of the space itself. It's related by some transformations. But when we try to apply it to extract some consequences which predicted by mirror symmetries, then we seem to have no progress at all. And so the plan is to employ the intrinsic properties of genus 0 Gromit invariants, intrinsic identities which are there. What was the state of that story by that moment? There is this Barannikov's geometric point of view on it. He calls this, what I call the small j function, call it Baker's function, yeah, so he says that it's kind of determines such a semi-infinite variation of Hort structures, but he's not interested in the properties of the function f node itself, the total, the big J function. Why? Because there is Dubrovin theory, which says that it's the reconstruction theory. It can be reconstructed from this one. If you know this one, or that matrix S, then it's reconstructible. And you look in the Dubrovin wrote in the year 92, I think some 1992, some 200-page book where in particular there is this reconstruction formula, which kind of, yeah, it's kind of strange looking formula, somewhat reminiscent to some Lejeune transform, or it's hard to say. So it's some complicated formula, and it employs topological recursion relations, which some infinite system of third order partial differential equations. And so the difficulties that we encounter were the following. we have this geometric description of transformations that transforms one Lagrangian section to another. And we want to combine it with some infinite system of some partial differential equations for the function that determines that. But how can you can combine them together? They formulate in completely different languages. That one is a geometric, some symplectic transformation, and the other is some infinite system of some partial differential equations or whatever it is. So therefore, the question is, okay, what's that? Okay, the Dubrovin theory says that from this J function, small J function, you can reconstruct the whole thing. What's the answer? How to reconstruct it actually? And here is the answer. So that's how you reconstruct it. You take this space z times t tau of which is determined by the derivative of it, and make it move with tau, and so what it sweeps, it is some Lagrangian cone, which is a graph of differential of that function that you want. That's reconstruction. That's Dubrovin's reconstruction theory. That complicated formulas which look like something like reminiscent of Legendre transforms. That's what it geometrically. So you so there is this moving ruling in dimensional space. It sweeps something Lagrangian, and that's a graph of differential of the function. Now we are in business because now we have this, so that it turns out that this infinite system of sort of the partial differential equations actually is captured by this properties, that L is an overruled Lagrangian cone such that its tangent spaces are tangent to it along z times the tangent space, and that's all. There is nothing else there. And now we are is formulated in the same language as our transformations that connects L and L bar. Connects L, Lx and so that transformations that this transformation and we can hope now to use the power of all of the things together to extract useful consequences. Yet it turns out that it's not enough. So we need one more thing, which is called the divisor equation. And that's what it is about. If in the diagram, so we take degree 2 class in X and pull it back to this modular space and push it forward. Similar to what we did with string equation, we pull class 1, and now take degree 2 class and push it forward. Then, cohomologically, then it will be constant, which is just what is it? It's the integral of the degree 2 class over our curve. So it is the component of the degree of our curves with respect to that class. And because we know the answer, then it puts some additional constraints on generating functions. And that's what divisor equations are. But we'll discuss it next time. So that's turns out that it implies some demodule structure and many other remarkable things. And altogether, they allow us to obtain a neat proof of various mirror formulas. But it should stop now.